So here, what's our problem? We can just scroll right down to the picture, right? Because proof by picture. So the input's a graph that's undirected. So this looks directed, but that's because the solution's in there, right? The input is a graph, and the rule is that every node has even degree. That means every node, the number of edges is even. That's the rule, and our goal is to find an Eulerian. I had to first say the guy's name. The guy's name is Euler, and so his path, or Eulerian tour, and what it means, it's a path that starts and ends at the same place, and it has to pass through every edge exactly once. All right, so it can't go through the same edge twice, and it can't miss an edge. All right, and so if we were doing so what's an obvious algorithm? You just start walking, right? I mean, that's an algorithm. It's kind of a more of the output algorithm, because the output is a path, and you're just producing it. So let's start at S and start walking, right? So maybe there are many edges out of S. I don't know what this picture is supposed to read, or it's just the picture is just the path I've done so far, right? So there are lots of edges, and I just started S and I walk. And the reason it's directed is because it's telling you which way I'm walking, right? And I walk and I walk and I walk and I walk, right? So that's the algorithm, right? And so it wasn't hard to define that algorithm, and when do you stop? Well, when you stop, when you've hit every node exactly once, and you're back where you started. I mean, that would be a great algorithm, right? But how do you know that happens, right? What can go wrong? Well, you think that what can go wrong is you get stuck, right? And what the stuck means, I can think of two ways that you can get stuck. The first way is you come to some node V, not the node you started with. You come to some node V, and and you've traveled on all the edges, right? You have to leave V along some edge that you've never been along, right? Because if you've been along it already, you're not allowed to go along it a second time. So if I arrive at V and there's an edge that I've never been along, then I go along it. But if I've been along all the edges, then I'm in trouble, right? So let's prove that never happens. I mean, how do you prove it never happens? That's a big statement, right? And it has to do exactly what Azil, is that right?
Azriel.
Oh yeah, there's an R in there. Sorry, I missed the R. My eyes are going, and Azriel. So he was saying, hey, well, why do we use we had the fact that every node had even degree, had an even number of nodes, and we're going to use that. And how do we use it? Well, we're sitting at V. Let's think about how many edges we've used, right? How many edges can we gone along that? And what do we know about V? All we know is it's not where we started, right? Because we'll talk, if we're at the start node, that's a whole different game. So we're at some node where we didn't start. Well, what could we have done? We could have entered the node and left the node, right? You enter it, you leave it. How many edges does that use? That's 2, right? and then you enter it and you leave it. That uses 2 more. You enter it and you leave it. That's 2 more, right? Those are all an even number of edges, the entering and the leaving. And you never can use the same one twice. So we know that's an even number of edges. But then at some point, well, we ended up at V. So you entered, but you haven't left yet, right? So how many edges can you have used up? Well, it's kind of a loop invariant, right? The loop invariant is that the number of, if you're not on a node, then and you're not on S, then the number of edges you've used is even because you've come in and you left. You came in and you left. But if you're ending at V, then the number of edges you've used is odd, because not only did you come in and you left a few times, but you came in and you're there, right? You didn't start there. Now, in fact, S is going to be odd because you started there and you left, right? That's one edge. And then you came and you left and you came and you left. So we can say, in fact, our loop invariant can say, no matter what path you have, where you started, if where you start and where you end are different, then where you start and where you end are both odd degree in terms of what you've used, and everywhere else is even because you've come and gone, right? Does that make sense?
Yeah.
Right? But we know that V has an even number of edges. So if you've used an odd number of edges and it has an even number of edges, then Euler says, magic, there's got to be an edge that you haven't used, right? And that guarantees that you're able to leave, right? Does that make sense?
Yeah. So how would we deal with the 0 case, since you like zeros so much?
Well, what's the other case? Oh, when you have 0 edges?
Yeah, so you just have like a single node, nothing else.
Oh,
Would
well,
that work within the same
if there's a single
algorithm?
node all flighting by itself, that's easy. We never have to go there, right? It doesn't say you have to visit every node. It says you have to visit every edge exactly once, right? So if this node has no edges, then you never have to go there.
Got it.
Right? You never have
But
to
we
go
can't visit an edge. No, we cannot visit an edge multiple times, but we can visit a node multiple times.
Of course. In fact, if a node has degree 8, you know that you have to come and leave 4 times. Right? Because some of the edges, half the edges you're going to visit by entering the node, and half the edges you're going to visit by leaving the node.
Okay.
Right? There's a famous puzzle, you may have heard of it, you're in Paris, there's a park, there's a pond, there are islands in the pond, there are bridges, right? And the task is for lovers under the moon to cross every bridge exactly once and start and end in the same place, right? That's a puzzle. Can you do it? And the answer is you can't do it. And why can you not do it? Is because there are 2 nodes, there are 2 islands that have odd degree. And so, you know, if you're going to visit every bridge once, then you got to start in a node that has odd degree. I mean, if there's an odd degree, you have to either start there or end there, right? And so you can cross every bridge exactly once, but you have to start in one of the nodes with odd degree, and you have to finish in one of the nodes with odd degree. So you can never get back to where you left your clothes. Right? Does that make sense? So now Euler is saying, if every node has even degree, then you can do it. right? Because you can keep going. Right? Does that make sense? Now, there's one other place that you can get stuck that we haven't talked about yet. Right? And that's B. So suppose you start at S and you do you do some walk, right? Maybe it oh no, here, I guess that's not oh yeah. So forget this edge to V. All right. Oh, that's a dotted line. See, the edge to V is dotted, so it's not part of our path. Right? So we did this cycle and we got back to S. Right? And now maybe there are no more edges out of S. Right? So we can't continue. The number of edges from S is even, but we've visited them all. Right? We left and we came back. And we visited an even number of edges. We visited them all. So we can't continue, right? But maybe, so if we were done, if we visited every edge, we would stop. But maybe there's some edge we haven't visited, right? So we're not done. So one of the requirements, here's another way you could not be done. Another thing Euler says is, well, suppose the graph isn't connected. Maybe there's some graph over here and some graph over here, and there's no edges going between them, right? Well, in that case, clearly you can't visit all the edges, right? Because you can't get from one component to the other. So Euler makes two requirements. He says that every node is even degree, but he also says that the graph is connected, right? So if it's connected and we've gotten back to S and don't know how to continue, and there's some edge way over here, see my mouse? There's some edge that we haven't gotten to, then I say you got to be able to follow, there's a path. My point is that there's got to be an edge like V that's touching the path that we've done and that you haven't walked along. Right? Why is that? Because if there's some edge way out here that we haven't walked along, then because the graph is connected, there has to be a path back to the stuff that we have walked along. And so you just follow that path backwards until you get to the edge that's touching what we've walked along that you haven't walked along. Right? Does that make sense? So if our graph is connected, then there has to be an edge from some U to some V that in which you've been to U, but you haven't walked along from U to V, right? Does that make sense? Everybody buy that has to exist?
Just to clarify, and we're saying that from that V back to the path we walked along is another path because we know it's equal, it's even, right?
No, we're not doing anything even now.
Okay.
I'm just saying, suppose there's some stuff you've walked along and some stuff you haven't walked along, right? Then, because the graph is connected, it's kind of like, were you there when we did the pearls that are red and green, red and blue? Remember that?
Yeah.
So suppose I have a necklace with red and blue pearls, and I know the first pearl is red and the last pearl is blue, then there has to be some edge where it goes from red to blue, right? And why is that? It's because it started off red. So if you keep walking along the necklace, it's red, 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 red. Well, it can't be red forever because it ends at blue. So at some point it has to turn from red to blue, right? So that's the same argument here. I know that there's some node S that I've been to before, and maybe there's some edge out here that I haven't been to before, and I know there's a connection, so I know that there's a path from where I have been to where I haven't been, right? So let's say that where you have been is red and where you haven't been is blue, right? So you just walk along, you just imagine going along that path as if it was the pearls from things you've been to the things you haven't been to. And at some point, there's a place where you go from I've been there to I haven't been there. Right?
Yeah.
That's all I'm saying. What is the property? There's this UV edge. And what is true about UV edge? So see, it's dotted, which means I haven't walked along it, right? I know I'm not done. Why am I not done? Because I haven't walked along it. Yet, I'm stuck because I'm back at S. So, I keep hearing this beep beep thing. And do I have Discord running that's beeping, or is it the chat that's beeping? Anybody know? Do you hear it? It goes beep beep.
I think it's your Discord.
It might be Discord, but you can disable that
Yeah.
in options.
Yeah, exactly. Do I have Discord? I don't know if I'm running Discord. Anyway, it just annoys me, the beep beep. So I'll worry about that later. So let's go back to what we're doing here. Nope, not that. That is machine learning. No, what are we doing? Oh, we're doing. Here we are. All right. So everybody get it. We found this edge, U to V, that we haven't visited. So what I'm going to do is I'm going to change. I have to edit the path that I have so far, right? Because I can't continue my path. So at S, I'm going to glue together the path. I'm going to glue where, I started on an edge and I ended an edge. And I'm going to glue that together to be one path. You know what I mean? And now what I have is I have a cycle. And then at U, I'm going to, at some point, since we've been to U, there's a place where we entered U and we left U again, right? So at that place, I'm going to cut the path, right? And so that's what I mean. I make U to be my new S. Now I pretend that the path started at U and went around this whole cycle and ended at U, right? But now the advantage is I can continue. I start at U, I come back to U, and then I continue along to V. And that is how I can keep making my cycle longer and longer, right? Does that make sense? Yeah. And so now we've kind of proven that until you're done, until you've seen every edge once, you're guaranteed that you can keep going. And that's kind of a loop invariant algorithm that proves that you can always find a Eulerian cycle. Everybody understand that?
Yeah. Also, Prof, is this question considered by you to be one of the hard questions or the easy ones?
Well, let me tell you its history. I started teaching a grad course, and in the grad course, I found, most grad courses, they teach really hard esoteric theory stuff, and the students didn't want to learn that. So I started teaching them what they needed to know, and what they needed to know was loop invariance, right? Most of the grad students come from foreign countries, and they didn't know enough about loop invariance, in my opinion. So I gave them a really quick summary of the 31-1 material. And I gave them harder examples. And so this was an example I gave them. They had a week to do it, and they were grad students. So would I expect you to figure this out in an hour and a half test? Not without a lot of hints.